All right, so here we are back with the agenda, and this will be our third talk of our second day of the Blockchain Community Day conference, and we'll be having three more talks after that. And I'm very happy to invite our today's guest speaker, Hayk Andriasyan, who is the senior security researcher at Hexens, and our today's topic is privacy preserving AI. Hi, Hayk, how are you?
Hey, great, thanks. How about you?
Yeah, me too. Thank you so much for joining. And while we are bringing your presentation to the stage, could you please
Mhm.
just tell us a couple of words about yourself and about your background and who you are?
As I said, my name is Hayk Andriasyan. I work at Hexens as a security researcher concentrated on Web3, Web2 security, also cryptography and AI.
All right. And that sounds amazing. I can see that your deck is on the screen. And
Mhm.
you're good to start. Good luck.
Thanks. So today I will talk about privacy issues and attacks in AI systems and how different cryptographic techniques can be used to mitigate them. Modern AI systems are no longer isolated models running on static datasets. Today, AI operates as a multi-stage pipeline. At every stage of the pipeline, data is transformed into different representations such as gradients, embeddings, activations. These representations create privacy leakage surfaces. And so the challenge is no longer just for the data, but how do we secure the privacy of the entire AI pipeline? AI system consists of multiple interconnected components. The core pipeline includes data collection, model training, inference, and output generation. Also, an additional retrieval pipeline is added through RAG architectures. The documents are transformed into embeddings stored in vector databases. The algorithms of machine learning and deep learning were originally designed without a defense mechanism against malicious threats in mind. And it was believed that black box deployment was a sufficient security boundary. So by wrapping a model in an API that only returns the prediction or confidence score, the training data was thought to be secure. But there are adversarial machine learning attacks on those systems. So before discussing the attacks, it is useful to define what privacy means in AI systems. Different parts of the system require different protection guarantees. For instance, training data privacy guarantees that the malicious actor will not be reverse engineer the training data. Input privacy guarantees that the user input data cannot be observed by other parties, including the model creator. Output privacy guarantees that the output of a model is not visible by anyone except the user doing the inference. Model privacy guarantees that the model cannot be stolen by a malicious party. And together, all this define the main privacy dimensions that AI systems must address. After understanding the main privacy problems in AI, we can look at how these leakages can occur and how attackers exploit them. For example, the memorization of training can cause privacy issues. Also, there are membership inference attacks, model inversion attacks, or model extraction attacks that also can leak privacy data. So let's look each of them. Memorization occurs when a machine learning model stores specific examples from its training data inside parameters instead of learning the general patterns. This becomes a privacy risk because the model can later reproduce or reveal parts of those exact training examples during the inference. In sensitive domains, this can lead to leakage of private information that never was intended to be exposed. Several factors increase the likelihood of memorization in machine learning models. For example, duplications in training data are most likely to be memorized. Larger over-parameterized models have more ability to store specific examples rather than just generalize the patterns. Also, longer training can lead to overfitting. In membership inference attack, the attacker tries to determine whether the specific record was part of the model's training dataset. Attackers create shadow models with known training data to learn to differentiate pattern between member and non-member samples. And this simple yes or no information can violate the privacy. And memorization is one of the main problems that can cause to successful membership inference attacks. The other attack is member model inversion attack. Here, attackers submit carefully crafted queries to the ML model, analyze prediction outputs, and through the repeated iterations, they are trying to reconstruct the sensitive features from the training data. At its core, model inversion is an optimization problem. The attacker treats the model as a mathematical function and attempts to find an input that maximizes the model's output for a specific class. It's like the opposite of membership inference attack, and here attacker asks what people in your dataset look like. And you can see in the picture from the right is the actual trained data, and from the left side is the recovered data. The next attack is model extraction attack, where adversaries repeatedly query a model API to learn how a model behaves. Over the time, they can approximate the original model, effectively stealing the intellectual property and sometimes recovering the memorized data. This is particularly relevant for public APIs. As we know, at the heart of RAG is a vector database. During retrieval, the system searches for vectors that are close to the query embedding. One important privacy risk is embedding inversion attack. Although embeddings are numerical representations, they can still preserve semantic information from the original data. In an embedding inversion attack, the adversary attempts to reconstruct the original input directly from the embedding vectors. For instance, we can see here that the user tries to embed I love fishing, how about you text. And the attacker, when he steals the embedding model, he creates the inversion model and recovers the text, I love fishing, do you? So you can see that the recovered text is not exactly the same, but meanings are close to each other. So now let's look how different defense mechanisms works. For instance, there are training time defenses. One major approach is differential privacy. Another approach is data sanitization, which focuses on removing or anonymizing sensitive information before the training begins. Finally, regularization techniques such as dropout, early stopping, or weight decay can help to reduce the overfitting, which also lowers the memorization and privacy leakage risks. Other common defense mechanism is inference time defense. One of them is query limiting. By restricting repeated queries, systems can reduce the risk of extraction and inference attacks. Output filtering also helps to detect and remove the sensitive information from generated responses before they are returned to the users. Beyond training and inference protections, privacy can also be improved at the architectural level. Federated learning is a distributed training approach where user data remains on local devices and only local model updates are shared with the central system. Another important technique is the trusted execution environments, which provide hardware-level isolation for sensitive computations. So let's look each of the techniques more deeply. Differential privacy is one of the most common approaches for protecting sensitive data. Its goal is not to completely hide the dataset, but to mathematically limit how much information any single individual can contribute to the final model. The core intuition is that if we slightly change the dataset, by example, for removing a single person's record or somehow change them, how the output of the algorithm will behave. In other words, the participant of single individual should not have a noticeable impact on the system's behavior. So the idea is illustrated in the figure. We have two datasets, D and D prime, and they are differing with one entry. And we have some randomized mechanism M, which is applied on both datasets. And from the picture, we can see that the probability distributions of MD and MD prime are almost the same. And because the outputs are statistically similar, an attacker observing the system cannot confidently determine from which dataset the answer was returned. And we can see here an epsilon parameter, which called privacy budget. And if the epsilon is small, the privacy is stronger preserved. But the stronger privacy we can cause to bad effects on the actual inference and accuracy. So differential privacy works by injecting some calibrated statistical noise into computations or training process on output or even on inputs. The noise hides the individual contribution while still preserving the overall statistical utility of the data. Depending on dataset type, gradient computation, model architecture, the privacy guarantee differs offered by each of the noise addition. And you can experiment with differential privacy frameworks like Opacus, Tensor Privacy, and maybe some others. Another privacy-preserving technique is fully homomorphic encryption. Homomorphic encryption itself is a cryptographic technique that allows computation directly on encrypted data. In traditional encrypted systems, data must first be decrypted before any computation can be performed. Homomorphic encryption changes this model. For example, a user can encrypt data locally, send only ciphertext to an external server, and the server can still perform computations without ever decrypting the data itself. After the computation complete, the encrypted result is returned to the user, who decrypts the final output locally. And there are several homomorphic encryption systems that are based on the computations they support. For instance, partially homomorphic encryption support only one type of operation. Either it can be addition or multiplication. Leveled homomorphic encryption supports both addition and multiplication with leveled computation circuits without requiring bootstrapping. But after some level of computation, the decryption fails. To overcome this, there is fully homomorphic encryption, which supports arbitrary computation on encrypted data. This means that complex programs, neural networks, even AI inference pipelines can be executed entirely in encrypted form. Also, there is another categorization of FHE. One of them is exact FHE, where every operation is performed in a precise way. And the result after the decryption is the same as would you get if computed directly on plain text data. Schemes like BFV, BGV, or TFHE fall into this category. The other one is approximate FHE, which somehow relaxes the exact precision. Instead of exact integers, it works with approximated real numbers, which allows to perform operations on floating point data. This is especially useful for machine learning and neural networks. The CKK scheme is one of most common example. And a key challenge in all FHE schemes is the noise growth. Every computation adds noise to ciphertext, and if that noise becomes too large, the data becomes unreadable. And there is a technique which is called bootstrapping, which refreshes the ciphertext by homomorphically decrypting and re-encrypting it, reducing the noise back to a usable level without exposing the plain text. So before discussing the private inference, let's look at the basics of large language models. LLMs are based on transformer architecture. The model receives the input prompt, converts it into embeddings, and processes them through multiple layers. Inside these layers, model uses self-attention, matrix multiplication, non-linear activation functions, and some probability transformations to learn the relationship between the tokens. One of the most important components is attention mechanism, where the model computes query, key, and value representation to determine which parts of the input are most relevant to each token. After the attention scores are computed, the softmax function converts these scores into probabilities. And this representation then pass through additional layers, producing probability distributions over possible next tokens for text generation. And from privacy perspective, this LLM architecture introduces a major challenge. During the inference, user prompts, intermediate activations, and attention computations are normally processed in plain text on the server. And as you can see in the diagram, to overcome this, we can use FHE, where we can encrypt the prompt, do a private LLM inference, and then the server returns an encrypted answer where the user can decrypt and read the result. For private LLM inference, mostly it is chosen the CKKS scheme, which is not exact, which is approximate FHE scheme. To perform private LLM inference, standard LLM components must be translated into CKKS-based operations. One of them is ciphertext to plaintext matrix multiplication. This occurs when multiplying the encrypted data by unencrypted model weights, such query key and value projections and neural networks. This operation is computationally cheaper and adds less noise. And another one is ciphertext to ciphertext multiplication. This occurs when multiplying two encrypted matrices together, such as when calculating the attention scores from encrypted queries and keys. And also, it must handle nonlinear blocks. For instance, the nonlinear functions like softmax activations cannot be computed natively in CKKS. They are approximated either some polynomials or replaced with simpler polynomial alternatives. And the encrypted operations can easily exceed the noise budget of CKKS, and that's why it is required to apply the bootstrapping technique to reduce the noise and restore back to the normal noise budget. Also, there is a real-world usage of FHE with machine learning. iPhones has a feature called enhanced visual search for photos, which allows a user to encrypted search their photo for specific locations. The client encrypts a vector embedding of the picture, send the picture to the server, and the server performs homomorphic computation to compute the nearest neighbor and send the encrypted result back to the device, and device decrypts it. Also, they use differential privacy with strong privacy parameters. And also they use some anonymization techniques to hide the IP address of the device. Okay, the next privacy preserving technique is federated learning. In classical machine learning, all training data is collected and stored in a central location. The model is trained on this centralized data set. Federated learning takes a different approach. Each device or client trains the local model on its own data. Only local model updates are sent back to the central server, which they are aggregated into a global model. So the key difference is classical machine learning centralizes the data, while federated learning keeps the data decentralized. This slide illustrates overall workflow of federated learning. It starts with a central server that initializes a global machine learning model. This model then distributed to the chosen clients. Each client receives the current version of the model, trains it locally using its own private dataset, and it is important that the raw data never leaves the device. After local training is completed, each client sends its update back to the central server. And the server does not use the data directly. Instead, it aggregates all the received updates with an algorithm like federated averaging. And after averaging, it sends back to the client devices. And this whole process repeats over multiple communication rounds. You can experiment with federated learning using the NVIDIA Flare or TensorFlow or Flower framework. Here in this computation can arise some privacy issues or trust issues. For instance, during the local training phase, client might introduce malicious models to disrupt the system. Or at the global aggregation stage, the trust issue also can arise. For instance, the aggregator can add malicious malicious updates instead of using the honest client's updates. And there is a ZKFL solution that overcomes this issue. We can look how that works. During each round, the client trains their models locally. Each client encrypts their weights using Pedersen algorithm. Then the client signs the encrypted updates. Then it sends the tuple of local model update, encrypted model update, and the signature to the aggregator. And the aggregator aggregates the received local model updates, generates the global model update. Then it computes the aggregated value of the encrypted global model update and signs it. After it, it generates a zk-SNARK proof of the computation and the encryption was done using only client's weights. Then the aggregator transferred the global model update and its encryptions to the clients and broadcast the proof to the blockchain. And if the proof is correct, the hash value of the encryption is written to the blockchain. And when the next round starts, the client reads the blockchain to check if the hash is appended on chain. Another approach of federated learning is decentralized federated learning. Although we can see that federated learning is decentralized training platform, but there is a problem that it has a centralized coordinator. Decentralized federated learning removes the need of that coordinator. Instead, the clients participate in P2P network where each device performs local training and directly exchange the model updates with each other. In some designs, it is used blockchain as a coordination layer, and smart contracts can be used to manage the training logic, ensure that only valid updates are included in learning process. But in terms of practical usage, decentralized federated learning based on blockchain are still experimental. And in general, the stronger privacy protections often reduce the model accuracy or system efficiency. And as it was said, for instance, adding noise through differential privacy can protect the sensitive data, but it may also decrease the model performance. Techniques such as FHE can provide strong guarantees, but they are still expensive in terms of latency and computation. And because of this, privacy-preserving AI is fundamentally an engineering balance between utility, performance, cost, and privacy guarantees. And there is no single mechanism that can completely solve the problem. Thank you. Questions?
All right. Thank you so much, Ike, for this amazing presentation. Let me just quickly go through the questions. And yeah, before I start asking questions from the live chats, let me just ask a simple question from myself. And yeah, I'm not that technical person, but still, for a normal person using some kind of AI tools, what is the number one thing that can leak? Is it my prompt or my files or the AI trading data or what else?
So, for instance, if you are installing some skills, they can be some malicious skills which can steal the environment variables, some private keys. So, yeah.
Mm-hmm. All right. And a question from the live chat. It says how hackers can steal model from API.
Yeah. Can I get back to the slide? I can show.
Sure. Mm-hmm.
Here, you can see that the adversary tries to do as many queries as he can, and he collects many key value examples where the key is the input of the model and value is the output of the machine learning model. And having this tuple, he can try to create its own local model, training with that collected data, and he can try to mimic the original model.
Mm-hmm. I believe that answers the question. So whoever asked it, feel free to ask any more details about it. And the next question says, what will be the best easy protection for startups? Rate limit, filter output.
Yeah.
And one more question, what is the first defense they should add along with rate limits, output filtering, or something else?
So, as it was said, for instance, use the differential privacy techniques, add some noise on training data, but it's like an experimental one. You cannot say which epsilon value is correct. You must try some different values and understand which is suitable for you. Also, yeah, you should add the rate limitings, output filtering. You can also use FHE or multi-party computations too.
Mm-hmm. And a couple of more questions. Differential privacy equals add noise, right? Does it
Yeah.
kill quality?
So it is a trade-off. You must find the correct balance between the noise and accuracy. When I showed the iPhone example, they also use the differential privacy there.
Mm-hmm. All right. And I think that was the last question. Thank you so much, Ike, for this wonderful
Thank you too.
technical presentation. Yeah, I think so far this is the most technical thing we had throughout the past 2 days, but still more to come. Really happy to host you and feature here on our conference, and really happy to see you again on our stage in the future.
Thank you too.
And yeah, after a very short 1 minute transition, we'll be back with our next speaker. So please stay tuned. And in 1 minute, we'll be on the stage.